All right, everybody, welcome to Unit 3, Lesson 2. As usual, you want to find the tasks for U3L2, either under assignments on Canvas or on the Science2 Canvas homepage, the weekly calendar. Got to scroll down to today's date, which is November 13th. You'll find it there. We're going to start off like we usually do with breakout rooms, sharing answer to some kind of silly question here. Let me make sure I have the right tasks to complete pulled up here. Okay, I'm going to throw it in the chat right now. The question is, what is the weirdest food you've ever eaten? Okay, share your answer to that. We'll come back together to share overall. Breakout rooms are open. We'll come back together in 2 minutes. Next on the docket was homework review. I'm just going to share my screen here for 2 seconds. Quizzes are looking good. You just had to make sure that you completed the Bob Gardner reflection with the graph. Most of you have, I'm seeing 12 attempts on this. So let me know if you need help. I'm also noticing a couple answers that are off from the correct ones. And so just a reminder that you have multiple attempts on these quizzes. So if you want to improve your score, just go and take it again. Just remember that if you type the response, you should back it up into a Google Doc or a Word document so that you can just paste it back in. You don't lose it on the second attempt. The reading quiz for chapter 26.1 through 2 also looks great. Seeing, let's see, nine attempts on that. So a couple people need to make sure you get that in. I like this little graph here. This is what we're going to focus on today, the layers of the atmosphere. But this last question, so was Bob Gardner close to space?
No, not really.
Not at all. Had a lot more atmosphere to get through. He definitely made it through most of the gases that are in our atmosphere, right? The gas concentration is highest in the troposphere and stratosphere. But yeah, he wasn't near space. And we'll talk a little bit today about why, getting a balloon up into space and whether or not that could actually work. So any other big questions or comments on those homework assignments or anything you found challenging? All right, we'll just do use some brief slides and some poll questions to review this content. So bear with me. I'm going to share my screen to my iPad really quickly. And we'll just go through 9 slides here. And I'll have some poll questions every 3 slides to see how we're feeling about stuff. Hopefully this is all pretty straightforward. All right, I'm going to hide everybody's tab here again. So just give me a quick verbal confirmation. Everyone's seeing the atmosphere in front of them on the screen?
Yes.
Yes.
Yeah.
Okay, so why the heck do I have a picture of a bowling ball over here? And it's just to emphasize how thin our atmosphere is compared to the size of our planet. If you think of Earth as a bowling ball, then the atmosphere would literally be the width of that sort of sheen, the lacquer that's on the surface, right? That's how thin it is compared to the overall size of our planet. And that's where all life exists on the surface of our planet as well. So the atmosphere is a very volatile place. There's a lot of things that change. Weather is the sort of day-to-day changes, right? This is something that can change rapidly. You can experience multiple forms of weather within a single 24-hour period or day. Climate is the general pattern of weather, right? So it's the trends, right? What's the rainfall per month? What's the average temperature per month? Both of these things can change. It's just they change on different scales, right? Weather is much faster. Climate is a more gradual thing and overall sort of trend or pattern. So that's a good distinction to make. We break Earth down into a bunch of different spheres, right? There's the biosphere, looking at where living things are found. The lithosphere, which is everything below our feet and Earth's different layers and magma and all that stuff. But again, we're going to start with the atmosphere and then work our way into these other layers later on. The atmosphere on Earth, and you guys went over this during your solar systems presentation, mostly nitrogen gas, which is its diatomic molecule, so it's actually N2. It's completely inert, which means that it doesn't blow up, it doesn't ignite or burn, it doesn't poison us. So it's just something we can exist in happily, and it's actually has probably contributed to a lot of the environmental stability we experience. 21% of the air you breathe is oxygen, which doesn't seem like that much, but our lungs are evolved to collect oxygen efficiently from that. And that's actually a good thing because unlike nitrogen, oxygen, O2, is extremely volatile, right? If it's exposed to any kind of accelerant, it will explode or burn. Right? The fire is literally a reaction with oxygen. It causes things to rust, right? The reason iron rusts is because it's reacting with oxygen in the air. So you don't want too much of this present. And then less than 1% is everything else, right? You hear about carbon dioxide all the time, argon, water vapor. Carbon dioxide levels are definitely increasing, but I don't think it's percentage-wise, there haven't been any huge impacts, though. I might be wrong on that. So all of these molecules of gas exert what's called atmospheric pressure, or what I like to think of as air pressure. And I know this is kind of a weird concept. But you have to kind of think like if you had a little stick figure here standing on the surface of the Earth, so this is at very low elevation, you have all of this air on top of you, right? I know it's weird to think, but you've got layers and layers, miles and miles of gases sitting on top of your head right now. And that's exerting pressure on you. So that's what we call air pressure, atmospheric pressure. Now, you don't notice it because we are evolved and adapted to live at the elevations we're living at. But if you were to go higher up, you would definitely start to experience some adverse effects, right? This is why people who climb Mount Everest have a bunch of different problems, right? Cerebral edema and stuff like that. But when you're up at these higher elevations, you're going to experience a lot less pressure, right? I'm trying to draw smaller arrows here. And so that causes gases that are inside of your body to also expand. This is why your ears pop when you're in an airplane, because there's less air pressure when you're at higher elevations. Bob Gardner had to wear that spacesuit because he went up extremely high where there wasn't very much pressure at all. And so he had to be inside his own pressurized suit so that his ears didn't explode and a bunch of other weird things might have happened. So the key trend to understand is that the density of air decreases as altitude increases. The higher up you go, the less concentration of air molecules there is, right? And so you can see here at lower elevations, you have a lot of air molecules packed together. At higher altitudes or higher elevations, they're much more spaced out. And again, this is due entirely to gravity, right? Gravity is pulling gases downwards, just like it's pulling us downwards. And so most air molecules are found closer to the surface of our planet at low altitudes, and there's less gas higher up. So air pressure outside has to equal air pressure inside. Hold on, I think I have a poll question. Yes, we are 3 slides in. So let me throw the first poll question at you. Should be on the screen now. See how you're feeling about this. All right, seeing 12 responses. There's 13 of us here though. So try to get it in. Again, this isn't graded, just take your best guess. It's also anonymous. All righty, here are the results. Very good, looks like we're mostly feeling good about this. So rain one day and sunshine the next, those would be weather patterns, right? Day-to-day change, pretty rapid. Average annual rainfall, of 18 inches in a certain location, that's a description of climate. So make that distinction between those two things. Okay, back to air pressure. So with these things in mind, as I mentioned earlier, internal pressure has to match external pressure, right? There's a constant sort of battle between these two things. You have a pocket of air inside your inner ear. As I mentioned earlier, when you fly high up in an airplane, external pressure goes down, and therefore since internal pressure hasn't really changed, the air is going to expand, right? This is why your ears pop when you're in an airplane. You can also think of it in the reverse. Scuba divers who are diving underwater experience a lot more external pressure because they're underwater, the water's weighing down on them. And if any of you have ever swum to the bottom of a deep pool, your ears start to hurt, right? Because you're increasing the pressure, external pressure, and it's actually crushing that inner ear space where the air molecules are in your sinuses. And so scuba divers actually have to be very careful about this. This is also why when you're scuba diving, you have to ascend very slowly. Because if you ascend too quickly, a lot of gas molecules that have been dissolved into your blood are suddenly going to become bubbles again, and they can collect in your joints. Does anyone know what that's called? A lot of scuba divers get it's very, very painful when you get air bubbles stuck in your joints. Want to take a guess?
Is it the bends or?
Yes, it's called the bends. Yeah, not something you want to experience. So you saw this change happen in Bob Gardner's balloon. Again, he at the beginning of his video, if you watch his balloon, seems pretty underinflated, right? It's not very large. Doesn't seem like something that could lift a capsule up. But as he rose in elevation up to 40 or 39 kilometers high, when you look at the video at the very end, his balloon is absolutely enormous. And that's because external pressure has decreased. And so the balloon expanded as a result of that. It was made of thin but very tough material, though, right? So they had expected and done some calculations about how much it was going to expand, and they honestly could have probably provided an even larger balloon. But again, we'll get at that with another question. All right, I just want to make sure that I am getting every 3 slides here. So I think we're ready for the next poll question. So here we go. Oh, didn't end that previous poll. Okay, poll question number 2. Give it a whirl. All right, seeing 11 responses. There are 13 people here. All right, looking good. Here are the results. Looks like most of you are feeling good about this. So why do your ears pop when you're in an airplane at 10 kilometers of elevation? It's because the lowered air pressure outside causes your inner ear to expand, right? The gases are expanding in there and pushing out past your eardrum. So that's what causes that sort of popping feeling and sound. Okay, 3 more slides here. Bear with me. Let's now explore the layers of the atmosphere. Again, you read about these. The most important one, and the one we're going to focus and spend the most time on, is the troposphere, because that's where living things exist. That's on the surface of our planet. It accounts for elevations of 0 kilometers to 12 kilometers. Temperature and density decrease as you rise. So as you know, if you were to climb the top of Mount Everest, which is pretty much as high up as you can go within the troposphere, at least walking, you're going to get very, very cold. And that's again because most of the gases are held towards the surface of the earth. And as we'll kind of get at in our next lesson, a lot of the warmth, right, the heat that's trapped in our atmosphere, the air, is actually radiant heat coming from the earth, right, that converted from the visible light. The next layer is the stratosphere. This one accounts for about 12 kilometers to 50 kilometers, so it's a little bit wider. But this is where Bob Gardner was, right? So that's why they call it the stratus jump. Temperature is a weird thing here. I mean, it's very cold, it's below freezing, but temperature actually starts to increase. It gets less cold as you go higher up in this layer. And I think that's partially due to ozone, right? This is where the ozone layer is. Ozone absorbs UV light, which warms things up a little bit. I think there's also some other gases present that are good at retaining that solar radiation heat. So I think that's why, again, it still stays below freezing, but it does warm up. It gets less cold as you rise up through that layer, which is a bit unusual. This is just same text, but a different diagram showing again, you can see temperature on the bottom, altitude as it's rising. So there's the temperature dropping as you get higher up in the troposphere, but then the temperature getting less cold as you rise up in the stratosphere. But once again, once you hit the mesosphere, then temperature drops down drastically. It gets much, much colder. This accounts for next layer, it's about 50 kilometers to 80 kilometers. So it's about as wide as the stratosphere. No solar radiation absorption here for some reason. I'm not entirely sure why. I think the gases are much more spread out. You don't have that ozone or anything else present that's good at absorbing a little bit of the heat. But then, and again, this is something that kind of boggles my mind, the thermosphere, thermo, think of meaning temperature, warmth. It is by far the widest one. It goes all the way to the top of our atmosphere and the edge of space. And according to this graph, it gets very, very, very warm. I think there's something unusual happening here, though, because the gases are so sparse here that if you were standing here, I don't think you would just spontaneously ignite. It's just saying that of the gas molecules that are present, they're moving very fast. But I'm curious, I don't entirely trust this curve here in terms of the temperature being that high. And again, Bob Gardner made it to this level here, which brings us to our final poll question relating to Bob Gardner and his balloon. Should be on the screen now. Give that a go. All right, got 13 responses here. Here are the results. Very good. We're all getting that it's no, but the reason why is actually the buoyancy, that there's just a certain point where the atmospheric, especially once it hit the mesosphere, it becomes so thin that there's no gas we could put in a balloon that would cause it to continue to rise. And I don't know about the bursting thing. I mean, it would also continue to expand. I think we could create a balloon technically that would be large enough to keep containing the gas, but you would eventually stop rising and run out of buoyancy. I think that's the primary cause. So that's why we can't just take balloons into space. It'd be pretty convenient if we could, but we're limited by it becomes so thin. It's also why you can't just fly into space, right? You can't just take a commercial jetliner, point it up, and fly straight into space because the air gets so thin that any kind of propeller engine isn't going to work anymore, which is why, does anyone know what actually takes space shuttles into space? They're not using like propeller-based jet engines, right? What are they using? What are those two big things that they attach to it? Starts with an R.
Rockets.
Yes, rockets have their own form of propulsion, right? That's what you need rockets to get through that very thin atmosphere and into space and getting fast enough to orbit. Any other questions or comments on those slides? All right. Now that we've talked about Bob Gardner's ascent and looked at the layers of the atmosphere, let's take a look at his experience when he was descending, right, when he jumped. So I have a little Ed puzzle there that I'd like you to complete. It's actually very short. It's only 3 minutes, but there are a whole bunch of questions you're going to need to answer relating to it. So this is tasked to complete step number 4. Please complete the Science2C. You guys are C period. Bob Gardner's descent Ed puzzle. I'm going to time for 10 minutes, so I'm hoping it won't take 10 minutes to complete it. I'll watch your progress and we'll come back together when it looks like everybody's or most people are done. If Ed puzzle doesn't work or freezes for you, as usual, I've got the original video on YouTube. You only have to watch the first 3 minutes. And there's a little Google form that has the exact same questions. Go for it. Let me know if you need help. I wasn't able to pull his parachute. Though maybe they had some automatic mechanism, I would assume they did. So what's happening to his airspeed? He begins to slow down quite a bit. If you were listening, and you could go back and forth on the video, but it actually should get louder. There's a lot more wind sound in the later part of that video. And so that brings us to the final question of why was his airspeed slowing down? And it's actually pretty sudden. I mean, there's a moment where his speed just suddenly starts to drop. What happened? Did he pull his parachute? Did anyone see the parachute? No, it wasn't the parachute. Any ideas? How'd you answer that last question? Nathan?
He entered, I think it's the troposphere, where the air is a lot thicker and the resistance was slowing him down.
Yep, so he transitioned from those layers, right? He went from the stratosphere, where air is very, very thin, into the troposphere, where it was much, much thicker, way more air drag began to slow him down. And it is pretty sudden. I mean, it's not like flipping a light switch, But it's very dramatic to see that as his elevation is dropping, there's a point where his speed suddenly slows down and things get a lot noisier because he's starting to interact with much thicker air. So kind of a cool demonstration again of just showing the layers and transitioning from one to the other. Any other questions or comments on that video? Would any of you want to jump out of a balloon from 39 kilometers up? Thomas is game. Anyway, who knows? Maybe that might become a recreational thing. All right, so we are now going to focus on that first layer. So I want to transition to focusing on the troposphere in particular, because this is where weather, climate, and all this stuff takes place. And in order to look at how things change in the troposphere, I'm going to introduce you to something called climagraphs, which look like this. Just going to do a very short introduction here and then have you do a little activity. They're a very cool way of kind of giving you a snapshot of the conditions within the troposphere in certain locations on the surface of our planet. So every climograph usually has a line right here. It's represented in red. That is representing average temperature. It's per month, so average temperature in January, February, March, and so on. It lines up with the scale on the right side, temperature in Fahrenheit. The green bars on the bottom are showing you precipitation, which is rain, snow, that kind of thing, per month again. And it's usually associated with that scale in inches on the left. And so you can see this is San Diego, California. January, February, and March are very rainy months in San Diego. It gets very dry in June, July, and August. It also tends to get very warm in those months, right? August is the warmest month. And so I like climagraphs because they give you this pretty cool snapshot. And they also allow for really easy comparisons. So for example, if we were to look at climograph from, I'm not going to say that right, Faya, Largo, and Chad, Kazakhstan, and Australia, you can see both similarities and differences, right? So notice precipitation is extremely low in most of these locations. These are definitely deserty places. But what's cool is look at the temperatures, right? So notice that Kazakhstan has very warm summers, May, June, July, and August, whereas in Australia, it's the exact opposite. It's very cold in May, June, July, and August. That's because Australia is in the southern hemisphere, so their summer is actually in January and December. So I just like these because they give you that little snapshot, allow for some quick analysis and quick comparison, and you're going to be doing a little worksheet where you're going to have to do that. You're going to be comparing two climagraphs, one of the San Diego one and another one of a mystery city that you will eventually figure out what that is. Oops, I lost didn't shrink out of that. So I would like you to do this in some form of partner work. I know it's kind of weird to do through Zoom, but I'm going to throw you in breakout rooms again. And what I'd like you to do is one person to be the reader, who is actually reading through the questions and the instructions out loud. And the other person's listening, and the other person is the timer. You're just going to keep track of time. Make sure you've both answered the questions before you move on. So I'll throw out a little announcement about the time. We're going to go for about 10 minutes once I have you in the breakout rooms, so you can figure out who's going to be the timer. Once you see who you're partnered up with, I'll blast out a little announcement about that. Work together on it, and we'll come back together to review after about 10 minutes. Let me know if you have questions. I'll be here waiting in the main room, and I might drop into a couple rooms too. So, all right, let me recreate the rooms to make sure everybody is in one. Okay, breakout rooms are open. Go for it. Oh, sorry, I was muted. Welcome back, everybody. Hope that was straightforward. Who figured out the mystery city? Where was it?
Chicago, Illinois.
Indeed, right? And it kind of makes sense, right? If anyone's been to Chicago or is familiar with the Illinois area, very cold and snowy winters, but then warms up quite a bit in the summers. So we're going to do a lot more with climagraphs over the next couple lessons. You'll be making a climograph on Google Sheets of your own local area and things like that. But we'll use that then to kind of step into more exploration of climate change, seasons, that kind of thing. So that's what we're going to be reading today. Homework for the weekend is going to be continuing reading in chapter 26. You're going to talk about seasons and Earth's tilt, as well as forget what the other thing was, but just looking at contributions for weather and that sort of thing. So stuff you might have gone over a little bit in PSI, so I apologize if it's a little bit of repetition. But usual deal, homework is to submit a photo of your notes, and there is a reading reflection you have up to 10 attempts on. Any questions on that? All right, it is Friday afternoon. We're a little bit early, but I'm okay with that. That's all I had for you guys. Thank you very much. Enjoy the weekend. I'll hang around if anyone has questions.
Thank
Thank
you.
you.
Thank you.
Thank you.